Hello friends. So today we are going to discuss three questions, and in these three questions, one question is from the year 2010 and we have two questions from 2011. So in totality there are three questions. So the first question, which was asked in the year 2010, and it's a pretty lengthy question, but the solution is quite short and simple for that. So it is given: electrical resistance of a certain material known as superconductors changes abruptly from a non-zero value to zero as their temperature is lowered below a critical temperature Tc naught. An interesting property of the superconductor is that their critical temperature becomes smaller than Tc naught if they are placed in a magnetic field, that is, critical temperature Tcb is a function of magnetic field strength B. The dependence of Tcb on B is shown in the figure. So this is given a figure. On the x-axis we have magnetic field, on the y-axis we have Tcb, critical temperature dependent on magnetic field, and the starting is our Tc naught, and it is almost constant for most of the region except for the higher value of the magnetic field. It drops suddenly. So based on this we have two questions on it. In the part A, it asks that in the graphs below, the resistance R of a superconductor is shown as a function of temperature T for two different magnetic fields. Solid line, which represents B1, and B2 is a dashed line. If B2 is larger than B1, which of the following graphs show the correct variation of R with these fields? And in part B, it is said that superconductors has Tc naught at 100 degree Kelvin. When the magnetic field of 7.5 Tesla is applied, as Tc decreases to 75 Kelvin, for this material, one can definitely say that we have to find out the relationship or a combination between the magnetic field and the critical temperature at a particular that magnetic field. So we start with part A. Or first, let's write what are the information given to us. Here the key information is that the B2 is greater than B1. So we start with part A, and in this part A we are given that there are two fields. So let us discuss for field B1, and this B1 field is smaller field. So for this particular field, or B1, we can write that resistance drops to 0 at a higher Tc B1, and for the second, that is for our B2, which is a larger field. In this we can write that resistance drops to 0 at a lower critical temperature that is dependent upon our B2. And these two conclusions are based on only one thing, that our B2 is greater than B1. So we can just summarize it. We can write that higher magnetic field, which in this case is our B2, this results in lower critical temperature. Lower critical temperature, or we can write that critical temperature at B2 will be less than critical temperature at magnetic field B1. Therefore, we can further write based on their resistance that B2 is represented as dashed curve in the options given. So we can say thus the dashed curve, which is for B2, should transition to 0 resistance at a lower temperature than the solid curve. And the solid curve is a representation of magnetic field B1. Therefore, we can say our B2 should be transitioning to 0 at the lower temperature. Okay, so B2, which is represented dashed, so at least B and D are straight away incorrect option. The only comparison is to be made between the option A and option C. But because of the magnetic field B2 is greater than B1, so based on the resistive property with respect to their magnetic field, you can say option number A is the correct one. You can say option A is correct. Now we come to part B. And part B, it is given that the zero critical temperature of a superconductor is 100 Kelvin. Yeah, it is given 100 Kelvin, and we are also given a magnetic field that is 7.5 Tesla. And this TC, critical temperature, decreases to 75 Kelvin. Then we have to find the relationship. So we are given that first point we are given as the zero field critical temperature, that is our TC naught, is given as 100 Kelvin. So basically it means that the material becomes superconducting, or we can say resistance drops to 0 when the temperature is less than 100 Kelvin. So this is the main conclusion from this statement. So we can write, this means the material becomes superconductor which basically means resistance drops to 0. Resistance drops to 0 when our temperature is less than 100 Kelvin in the absence of magnetic field. In the absence of magnetic field. Now we come to the second point. In the second point, it says that when the magnetic field is taken as 7.5, the critical temperature is drops to 75 Kelvin. Under B is equal to 7.5 Tesla, TCB, right? Critical temperature drops to critical temperature drops to TCB, which is given as 75 Kelvin. So it means that increasing the magnetic field lowers the critical temperature. So this means increasing magnetic field lowers critical temperature. Therefore, from here we can draw two important conclusions, that TCB decreases with the increase in the magnetic field, which is clear from the graph also. TCB decreases monotonically with increasing magnetic field. So we can say that higher magnetic field suppresses superconductivity. Higher magnetic field suppresses superconductivity. Superconductivity and requiring even lower temperatures to maintain zero resistance. Zero resistance. So let us check one by one the options that are given to us. So option A, it gives us that magnetic field is above 5 Tesla and the critical temperature at that particular magnetic field is given as 80 Kelvin. And partially from the graph, we know that our magnetic field is 0 Tesla when the critical temperature is 100 Kelvin, and from the given data it is that B is equal to 5 Tesla and critical temperature is our 7.5, 1 second, yeah, 7.5, not 5. And it is equal to 7.5 Tesla and the critical temperature is our 75 Kelvin. Now we come to the given two values. So we can see from the value of magnetic field, the optional magnetic field B, that is 5 Tesla, lies somewhere between 0 Tesla as well as 7.5 Tesla. Therefore, the temperature, that is critical temperature, also should probably lie between the 100 Kelvin and 75 Kelvin. Okay. So we can write that given option B is equal to 5 Tesla lies between 0 Tesla and 7.5 Tesla. Therefore, the TCB should lie between 75 Kelvin and 100 Kelvin. And please keep in mind, here in the question itself, it is asked that what we can say definitely. Okay, if there are any doubt, then that option can be neglected. Okay. So this particular option, we are not very sure that is true or not. So therefore we can say the 80 Kelvin is plausible but not definite. Therefore, this option is incorrect. Now we come to the option B. In option B, once again the magnetic field is given as 5 Tesla and the critical temperature is lying between 75 Kelvin and 100 Kelvin. And so same discussion between, for this particular range, this will be our fixed data and we are going to make a comparison for, let us call this as 1. So I can say from 1, B is, that is given B equal to 5 Tesla is less than 7.5 Tesla. Therefore, you can say the critical temperature must be higher than 75 Kelvin but lower than 100 Kelvin, and this is given exactly in the option of with respect to the critical temperature. Okay. So we can say that this is definitely true. This is definitely true. So option B is correct. Option B is correct. Similarly, we go for option C. In option C, we are given that the magnetic field is about 10 Tesla and the temperature once again is lying between 75 and 100 Kelvin, but the magnetic field is about 10 Tesla, that is greater than our 7.5 Tesla. So the temperature must be lower than 75 Kelvin. Once again we say from 1 B, that is 10 Tesla, is greater than 7.5 Tesla. Therefore, TCB must be lower than 75 Kelvin. So this option is incorrect. Option is incorrect. And now we have our option D. And in option D, we are given that the magnetic field is about 10 Tesla and the critical temperature is exactly at 70 Kelvin. Therefore, we can say from 1 our TCB at 10 Tesla, which is the given value of the magnetic field, given in the option, this is likely less than 75 Kelvin. And once again, we cannot for surely or definitely say that this condition will be true. We can say this value of 70 Kelvin is plausible but not guaranteed. But not guaranteed. Therefore, this option is not true. This option is not correct. Thus, the only option correct is option number B. So option number B is correct. Rest of all the options are incorrect. And now we come to the next question. Here it is asked that we are given, it was asked in the year 2011, and it says that a long insulated copper wire is closely wound as a spiral N of N turns. The spiral has an inner radius A and outer radius B. The spiral lies in XY plane and is steady current I flows through the wire. The Z component of the magnetic field at the center of the spiral is. So we are given a figure. Center lies as the origin and inner diameter is our, inner radius is our A and outer radius is given as B, and it is given that it is a tightly wound spiral. So we can treat these individual spirals as a circular ring, okay, because of the tight wound. Therefore, we can say that the spirals can be treated as concentric circular loops. Concentric circular loops. and there are n circular loops from radii A to B. Therefore, there are n circular loops with radii from A to B. Now we can use Bite-Savart law using for one circle loop, and then we can just integrate and find the value. Therefore, we can say Z component of magnetic field at the center of single circular loop of radius r, carrying current I. We can write it as dBz is equal to mu naught I upon 2r. Now we can find out total number of turns per unit radius. Total number of turns per unit radius, and the radial distance rather, will be from B minus A, because that is the only inner radius as well as outer radius. So we can say the spiral has n turns spread over a radial distance that is B minus A. Therefore, linear turn density or we can also say number of turns per unit radius. Number of turns per unit radius, we can represent it by small n, that will be equal to our capital N and B minus A. Now we consider a small portion dr and a small, you can say, number of turns as dn. So we consider infinitesimal contribution from a thin ring. We consider infinitesimal contribution from a thin ring with width dr, and for this the number of turns number of turns in dr, which we just consider, we can write that as dn is equal to n multiplied by dr. We substitute value of small n, we get our capital small number of turns will be equal to n b minus a times dr, and the contribution of these number of turns, so we can say therefore the magnetic field due to small number of turns, we can write this as dBz will be equal to mu naught I upon 2r and multiply by dn. We substitute value of dn, we get this as mu naught I upon 2r, and we have n b minus a multiplied by dr. Now we find out the total magnetic field for the entire spiral. Total magnetic field for entire spiral, let us call that Bz. That will be integration from a to b, and we have here dBz, and which can be further written as substituting the value mu naught I n divided by 2b minus a, and here we have dr upon small r. Now it is quite simple, straightforward integration. So we get our Bz will be equal to mu naught I n twice b minus a natural log b upon a. So if we check the options that are given to us, the option number A will be the correct one. Option A is correct. Come to the next question. It was also asked in the year 2011, and it says that an electron and a proton are moving on a straight parallel path with velocity v. They enter a semi-infinite region of uniform magnetic field perpendicular to the velocity. Which of the following statements is or are true? So we are given, we have two, you can say, charges. One is our electron, another one is our proton. And the key is that here the mass of the proton and mass of the electron, they have a considerable amount of the difference between them. So because of that, how they behave inside the magnetic field changes entirely. So we can just draw a rough approximate diagram for that also. Let us suppose this region, and here we have a magnetic field which is into the paper. So this is a magnetic field B, and first is given as our electron, and then we have our proton. We have two this. So we can draw a rough approximate figure for that. So if we have electron, let's draw for the proton first. So it enters, suppose, at an angle of theta, with this vertical line, which is a boundary line, then it will be forming a loop inside the magnetic field like this, and it will be going out from here. And this is a part of a circle. So let us suppose the center of circle is somewhere here, and if we join them, this angle will be also theta. So this internal angle will be also equal to 2 theta, and this is the direction of the velocity of this proton. And we have our electron, and electron enters somewhere like this, and this angle is given as theta. So inside it is going to follow this close to circular path like this, and finally it is going to leave the electric field. So we have electron enters in this direction and leaves from this direction, and here we have angle theta. So if center is, and we join them, we get this is angle of 2 theta. So this is our, you can say, path of electron and proton inside the magnetic field. So you can say path of electron and proton in the magnetic field. Now from the figure, we can clearly understand that both enter and leave the magnetic field with an angle of theta, same angle of theta. So you can say both enter magnetic field with same angle theta, and since they have different charges, they are deflected in opposite direction. So second point, they have different charges, so deflected in opposite direction. Opposite direction. And third is they leave the magnetic field with the same angle theta. They leave magnetic field with same angle theta, and the velocity will be also same. Input velocity will be equal to the output velocity. Okay. Thus, from here we can draw one important conclusion, that both electron and proton will come out of the magnetic field. You can say both electron and proton will come out of magnetic field along parallel paths, because it is clear from the figure also, along parallel paths. And so we can say the option A is incorrect because it says that never come out, and option B is the correct one. So we can say that option B is correct. Option B is correct and option A is incorrect. Now let us find out a part with respect to the time. They come out the same time or they come out in the different time. And we know that our time is equal to distance oblique speed, or we can say T is equal to D upon S. So therefore, let us consider for proton, and for proton we can just modify the formula as just writing the P for proton. But from the figure you can see the distance of the proton in the magnetic field is the length of arc it makes inside the magnetic field. Okay. Here the distance is with respect to the arcs. You can say the distance traveled by proton in magnetic field is the length of the arc it make inside the magnetic field. It make inside magnetic field. And we know the length of arc is a product of angle as well as radius. Length of arc is equal to angle multiplied by radius of arc. And from the figure we can say that the angle of the arc is proton is 2 theta, angle of arc is 2 theta, and let us call that radius is our r times p. Therefore, and the velocity is v. Velocity is v. Thus, we can write that for proton the time will be our 2 theta multiplied by rp and velocity v. Now we can find out the radius. Radius is quite simple. It will be a balance of, you can say, centripetal force as well as force because of the magnetic field. So that is quite straightforward. So we get this as mp v divided by E, and we have here B as a magnetic field. Therefore, we can write our time period equation. This comes as 2 theta v multiplied by mpv divided by E multiplied by magnetic field. And here v goes with v, and this gives us that time period for proton is our 2 theta multiplied by mass of proton, charge on proton, and the given magnetic field. Similarly, we can find out for our electron also. The only difference will be the angle of arc. In case of electron will be 2 pi minus 2 theta. Now is for our electron. So we can write the angle of arc is equal to 2 pi minus 2 theta, and let us call radius as our RE. Radius is our RE. Therefore, we get TE is equal to 2 pi minus 2 theta radius divided by velocity v. Once again, for radius E, we are going to have same equation but with respect to now electron. Therefore, we get the time period for electron will be about 2 pi minus 2 theta v multiplied by MEV divided by E magnetic field. Velocity gives velocity, and we get this as 2 pi minus 2 theta, and this is our EB multiplied by mass of the electron. So at least we are very sure that both the time periods are not same. So it means the time period is not same. So option number C is incorrect. So option number D is automatically correct. They will come out at different times. So we can say that our TP is not equal to TE. Therefore, option, which one? Option C is incorrect and D is correct. Option C is incorrect and D is correct. So these were 3 questions which was asked in the year 2010, and 2 questions were from year 2011. So this completes today's questions. Thank you.